So let's talk about implicit differentiation. A function is defined implicitly when it is inside an equation with other x's and y's all floating around, or x, y's, and z's. So let's remind ourselves, back in Calc 1, when you had something like this, to find dy dx, you would take the derivative with respect to x. So you would get 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y. Then you would have to bring the dy dx to one side, everything else to the other, suck out the dy dx, and then divide by whatever was attached to the dy dx. Everything's divisible by 3, so my OCD-ness makes me, not divide correctly. Let me just fix that real quick. Think. So now we're in multivariable. There's another way we can do it. Check this out. Again, we've got x cubed plus y cubed equals 6xy. We're going to find dy dx. We're going to define a new function, big F of x comma f of x, where that f of x is really our y. And my big F function is defined to be x cubed plus y cubed minus 6xy, which is just the original equation with a 6xy pulled over. We're going to use the next third dimension to kind of help us find a new formula for this. Now the key is, I know that this function has to be equal to 0, which means its derivative has to be equal to 0. So how would I find the derivative? Well, I'm going to use my chain rule formulas. I have the partial of f with respect to x times dx plus the partial of f with respect to y dy dx. Now, clearly, dx is 1. Dy dx is what I'm looking for. I will solve the equation for that and get this equation. Negative the partial of f with respect to x over the partial of f with respect to y. So shorthand, big F of x over big F of y. I want to find dy dx. On top, I have the partial with respect to x, so I get 3x squared minus 6x. On the bottom, I have the partial with respect to y, so I have 3y squared minus 6x. Again, don't like that everything's divisible by 3, so let's fix that. Now this doesn't look like what I had before. Wait a minute. Notice there's a negative in front, and when I run the negative through the top, I get the same expression. What about in one more dimension? Let's say we have this relation. In this case, z is being implicitly defined by your x's and y's. And we want to find the partial of z with respect to x, and we want to find the partial of z with respect to y. I'm going to pull the same trick. I'm going to define a new function, which is this expression with the 1 pulled over, and I just have to remember to set it equal to 0. So if I want the partial with respect to x, I have this, partial f partial x. I'm not going to read it. Again, I get tongue-tied. So I get this expression. Again, notice that dx is 1. The partial of y with respect to x is 0 because y is not x, and we treat everything that's not an x as a 0. So plugging that in, I'm only left with these 3 expressions. And I want to solve for the partial of z with respect to x, so I get this equation. If I go through similar steps, I'll get that the partial of z with respect to y is negative partial of f with respect to y over partial of f with respect to z. So let's finish this problem. I have yx cubed plus zy cubed plus xz cubed plus 2xyz equals 1. I'm going to write that as a function of xyz, setting it equal to 0 after I bring the 1 across. I need the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. So let's knock those out. With respect to x, I get 3yx squared plus z cubed plus 2yz. With respect to y, I get x cubed plus 3zy squared plus 2yz. And with respect to z, I get y cubed 3xz squared plus 2xy. So the partial of z with respect to x, I get this monstrosity, which I'm not going to read aloud because I will screw it up as I try to read all those x's and y's. And the partial with respect to y is this expression. That's how we implicitly find our partials given an equation where all the x, y's, and z's are all mixed together.